Okay, so we're going to look at section 7.4, and the goal with trig identities is basically to take something that looks like that and simplify it. Okay, a lot of times you can take something that has multiple trig functions and make it so it has less, okay, maybe just one. Okay, and we might even be able to get rid of that fraction as well. All right. So just as a reminder, an identity is an equation that's always true. So when we're using any of these formulas, we put just an x here. X can be anything. These are identities that are always true, regardless of any value you use for the angle. Okay, it works with a 30-degree angle. It works with a 76-degree angle. They're identities, so they are always true. All right, and as I already mentioned, you should be familiar with the reciprocal, the tangent, cotangent, and Pythagorean identities. They're the ones I just had up on the screen. We've worked with everything except the Pythagorean identities. Not in depth, but a little bit. There's a couple of the identities. Those are the tangent and cotangent. The rest of them are on page 403. So if you go to page 403, you'll see the same picture I just had up on the screen. That's one of the Pythagorean identities. But again, the rest of them are all on page 403. So the goal with trig identities, it's really just substitution. You're plugging something in for something, and you're hoping that somehow things cancel out. That's the goal pretty much every time. So this, you don't have to write this, but the idea of why you would simplify a trig identity is that in calculus, a lot of times you have to take a formula like that and do something with it. But if you can take this and simplify it, maybe get rid of the fraction and get rid of one of these trig functions, then you're going to have something easier to work with. All right? For our purposes, once we simplify it, we're going to stop. But in calculus, once you simplify it, the next step would be to take what you simplified and then do something with it. Okay, do some calculus with it. Okay, but we're not doing that step. All right, so one very basic trick that does work a lot of the times is to take everything in the problem and change it to sine and cosine. There is a way to write every single trig function in terms of just sine and cosine. Okay, you can write cosecant as 1 over sine, secant as 1 over cosine. Tangent you can write as sine divided by cosine, and cotangent, cosine divided by sine. Okay, so there's a way to take all 6 trig functions and write them with just sines and cosines. And sometimes when you do that, things cancel out. Now, this trick doesn't work all of the time. There are some problems that it doesn't work on, and figuring out which ones it doesn't, it's really just practice. But I would say most of the time, this is a good trick to try. All right, so let's try this one. All right, so we're going to try to change everything here into sines and cosines. All right, so let's start with cotangent. Zach, can you tell me how to rewrite cotangent in terms of sines and cosines?
I don't remember off the top of my head.
You want to help out, Trevor? Yeah, it's cosine over sine. Okay. If you're looking, you probably put these in your notes. I know it's in chapter 6. It might be section 6.2. I don't think it's 6.1. It's either 6.2 and then 6.3 I think was graphing. So I don't think it's that. I think we did it in section 6.2. That's where your formula should be. If somebody finds them and can confirm that, that would be helpful, but we don't need to know for now. Yeah. Yep. Cosecant is 1 over sine, so we just substitute it in. And now we're dividing fractions that have the same denominator. So what happens to the denominator? It cancels. Some people take and multiply by the reciprocal. When you divide fractions, if you do that, that's basically what will happen. And what are you left with? Just cosine. So taking the cotangent and dividing by the cosecant for any angle is the same as just taking the cosine, which is a lot simpler than this.
They're in 6.2, part 2.
6.2 part 2? Okay, thank you. Okay, now that's a pretty easy identity. Okay, that's a pretty straightforward one. So is this one. Let's try this. All right, so we'll again try changing everything to sines and cosines. All right, let's start with cosecant. Okay, how can you rewrite cosecant? It's the same way you'd have to type it in on the graphing calculator if you're going to graph it. Yeah. So 1 over sine. And how can I rewrite tangent? Sine over cosine. And anytime you're multiplying, you can cancel if the same thing is in the bottom and the top. You cannot do that with addition. So if this was like a plus here, you can't cancel top and bottom. Or a minus. You can't do that. But if it's multiplication, you can. So I'm left with 1 over cosine. And what's 1 over cosine? Not sine. Secant, yeah.
Yeah.
Right? So again, we took something that was a product, 2 different trig functions, and then we got rid of the product, and now we made it 1 trig function. This would be a lot easier to do calculus stuff with than the original problem. Okay, but for us, that's just where we stop. Any questions on that one? All right. This one, I'm not going to go through and do it, but it's a little different. It says to show that what's on the left is not equal to what's on the right. Anybody think how you could show something is not true? David?
Add a different thing to both sides.
Well, don't add anything else to it.
All right.
Just keep what you have there. But how could you show that what's on the left is not the same as what's on the right? Amanda?
Would you just simplify the one thing, like the one on the left?
Okay, you could try to do some algebra with the one on the left and see if it ever comes out to what's on the right. But there's a way to do it without even using algebra. Yeah? Sure, you could plug in a specific number. To show something is not true, you only need to show that it doesn't work in one time. That's it. It's like a counterexample. So the easiest way for me to plug a number in is just use the table on the calculator. And when you plug a number in, you want to be careful that you don't plug in something special. Like it might work for 0, but that just might be a coincidence that it works for 0 on both sides. You want to pick a number that's not special, like 0.26 or something. Okay, pick something that wouldn't probably be a special number. So 1 plus sine squared. And we're going to divide that by cosine squared. Okay, I might have put an extra parenthesis, but I don't think I needed it, but I don't think it's going to hurt anything the way I did it. But I didn't need it. And then cosine. All right, so if I do zoom 7, we can look at a picture of it. Okay, so that's the one on the left. There's the pattern. And the one on the right. So you have to be careful, because if you picked the right value, it would look like they're the same. For example, if you picked 0, you might say, oh yeah, what's on the left and what's on the right come out the same. Yeah, it's the same function. Nope, it's only the same at that one point, and again, at that one point, and that other point. So if you pick something other than 0, try like 0.28, now we can see, okay, they're different. So there's there's a counterexample. And you could also, if you had a graphing calculator, you could use that as evidence too, saying the graphs don't look the same, so they can't be the same. Even though they are the same at a few points, but not in general. Okay, so we don't usually have to do something like that a lot, but if you have to prove something false, just give a counterexample. Right there. All right, so the first two problems that we did, not the last one, that one was a little different, but the first two were what we call simplified. So in a simplified problem, they start you off with something like that. And you just simplify it as much as you can. You really don't know where you're supposed to stop. You just keep going till it looks like you're done. And I would say this looks like we're done. There's nothing else you can do. It's a single trig function. It's not a fraction. So you're done. Well, verify is a little bit different. Okay, I'm just going to skip ahead to show you what a verify problem looks like. That's a verify. Verify basically tells you something you're going to start with, what it's supposed to finish as, and now you have to figure out how. So it's like they give you a little more information than a simplify. They tell you where to start. They tell you where to stop. You just have to figure out how to get there. Okay. That's why I kind of like verify a little better, because you kind of know when you're done. Simplify, it's a little bit more vague. When have you done that problem? You know, they don't tell you where to stop.
Didn't we have a verifier as like a bonus question or like a test question?
We did have a question. I'm not sure if it was simplify or verify, but we did have a question on a test. Yep. So in general, when they ask you to verify, the best thing to do is start with the side that looks more complicated. Okay. It's easier to take something that looks complicated and simplify it. So it's easier to start with this and try to simplify it to sine. Don't start with something simple and try to make it look more complicated. That's a lot harder to do. Okay, some people work with both sides at the same time. I'm not going to do that because it starts to get confusing. But in the end, with a verify, the goal is you have a left-hand side and a right-hand side. They have to match. Okay, so I think we're going to do one more simplify, and then we'll try that verify problem. All right, so the first big trick I showed you for simplifying identities was to change to sines and cosines. Sometimes that doesn't work, or sometimes you have a problem where everything might already be sines and cosines. So we need another trick. Okay, another trick is to find common denominators. Okay, so remember, if you've got fractions like a over b plus c over d, a, b, c, and d could be numbers, they could be trig functions, it doesn't matter. But what's the common denominator there? BD, yeah, you take the two denominators you have, you multiply them together, and then to get the common denominator, you have to multiply each fraction by the other one. So you'd have to multiply this by d over d, and you'd have to multiply this by what? b over b. And now you've got the common denominator. And you can do what's in the top. If it's numbers, if it's trig functions, a lot of times there's nothing you can do. You just write whatever it is times the other thing. Okay, but keep that idea in mind. That's how you find common denominators. Just take the two that you have, multiply them together. So this doesn't look like a problem where you're going to need a common denominator, but it might come up all of a sudden. Okay, what property do you think I can use here that we use with numbers all the time? Yeah, pretty much anything you can do with numbers, you can do with this. Okay, so just distribute out sine. Now, some people, when they distribute it, they're going to change to sines and cosines at the same time. I'll just distribute it. So you'd have sine times cotangent plus sine times tangent. Now, what could I do with that? Huh? All right, so change cotangent to, what did you say? Cosine over sine. And if you want to make that sine a fraction, you can always just put it over 1. Plus, I've got sine again, which if you want to make it a fraction, put it over 1. And how about tangent? Yep, you can write that as sine over cosine. Now, what does the first term simplify to?
Cosine.
Yeah, just cosine. You can always cancel across the multiplication sign, never across an addition sign. All right, so we get cosine. No denominator, so if you want to put one, you could just put over 1. Plus, what's in the top of my fraction on the right?
I don't know what I'm talking
The right side.
On the right side, yeah. What's on the top?
Side.
Nope,
I said, yeah,
sine squared.
about. Yeah, just speak up.
So sine times sine is sine squared. What's on the bottom? Cosine. All right, so now we've changed everything to sines and cosines. There is more simplifying we can do. But changing to sines and cosines won't help. It already is. So what do you think I can do now?
Do the thing with the same.
Yeah, find a common denominator. And our hope is when we do that, that something cancels out. Okay, something nice is going to happen somehow. So what's my common denominator here? Yeah, it's cosine. The fraction on the right already has a denominator of cosine. So I don't need to change it. What about the fraction on the left? Yeah, you've got to multiply top and bottom by the other denominator. So that gives me cosine in the bottom. And what does that give me in the top? Cosine squared. Now, there's something there we need to recognize. It's one of the identities we haven't used before. I think it's the first time we've used it.
Pythagorean identity, where sine squared plus cosine squared equals 1.
Yeah, so if you go back and look at Pythagorean identities, sine squared plus cosine squared equals 1. Now, ours doesn't say sine squared plus cosine squared. It says cosine squared plus sine squared, but that's the same thing. Okay? You can take these identities and you can move things around and rearrange them. Like you could subtract cosine squared to the other side, and it's still the same identity. Right? So that entire numerator is going to turn into what number? That's just 1. And you could argue, well, should I stop here? I would go one more step. I would say something without a fraction is simpler than something that is a fraction. So what would be the answer there? Secant. Right, so we took a problem that was pretty complicated. It had 3 different trig functions. It had a distributive property and addition. And we took that whole thing and turned it into one function, secant. Right? Much, much easier to work with than the original problem. All right, so now we're going to look at some verifies. Okay. Again, what's nice about the verify is I know what I should get in the end. Okay. I should get sine. So once I get sine, then I'm done. And I circled the side that I thought looked more complicated. So we're going to start with that side. And we're going to just leave sine alone. Okay. Any suggestions what I can do with this one? Yeah, and how about the top too? We could change everything.
What over cosine?
Yeah. Now that way will usually work. Sometimes it's kind of like cleaning a car with a toothbrush. It's not the best way. It will eventually work. Okay, but so let's try it because we don't really know anything else to try. So it's all we can do anyway. So the top becomes 1 over cosine. Okay, the bottom, what did we say tangent is?
Sine over cosine.
So sine over cosine. And what about cotangent? Cosine over sine. Okay, so we've changed everything to sines and cosines. What could I do next?
Cancel out the sine, cosine.
Yeah, there's nothing that cancels out in the bottom. But we could focus on the bottom and try to do something with that. What could we do with what's in the bottom? Yeah. So at this point, I'm not sure if that's the best approach, but we're just going to kind of ignore what's in the top. It's just going to stay there for like the whole problem. And let's just change the bottom to a common denominator. Okay, what's my common denominator?
Sine times cosine.
Yeah, sine times cosine or cosine times sine, however you want to write it. What is the numerator, the first numerator missing to make it the common denominator?
Sine.
It's missing the sine, right? Or I should say the denominator. It's missing the sine. So we got to multiply top and bottom by
Sine.
sine. So what will that give me on the left?
Sine squared.
Sine squared. What's the denominator on the right missing?
Cosine.
Cosine. So we have to multiply top and bottom by cosine. So what's that going to give me for my, yep, cosine squared. And now, what can we do with that bottom piece? It does simplify, and it's something we've already used once today. Yeah. Sine squared plus cosine squared equals 1. Okay. So now I don't have any more addition. I'm just dividing a fraction by a fraction. How do you divide two fractions? So can you go ahead, tell me, Grayson, the whole thing? What would I write down to do that? 1 over cosine. Times sine cosine over 1. And I have a multiplication sign, so I'm allowed to cancel. And what am I left with? Just 1 times sine. Okay, chances are if you just make up a trig identity, it's not going to simplify that nice. Okay, every problem I'm giving you simplifies somewhat nice. And we got sine way back at the beginning. That's what we're supposed to get. So we verified that what's on the right does equal what's on the left. All right, so the third and last big trick that we can use, we can change to sines and cosines. We can find a common denominator. The third thing is to use the conjugate. And it doesn't say where the conjugate has to be. So conjugate usually looks something like this. This is the kind of problem where you would use a conjugate. Everything's already sines and cosines. Everything already has a common denominator. But any term that's a number plus or minus a trig function, you have a conjugate. So the conjugate of this becomes that. It's kind of like when we did imaginary numbers. 2 plus 3i, 2 minus 3i. Those are conjugates. 1 plus cosine, 1 minus cosine. Okay, or back in algebra 1, if you multiply x plus 3, x minus 3. What would happen if you FOIL these out? X plus 3 and x minus 3. What happened? Tom, what happens when you FOIL these out?
X squared minus 9.
Shouldn't there be a middle term, though?
A.
Now, what happens when you FOIL that out? Because then we're going to do it with trig in a second. Yeah.
Middle term cancels out.
Right. Whenever you FOIL conjugates, there is no middle term. Right. You get x squared minus 3x plus 3x. That's gone. So that's why you use a conjugate. It causes things to cancel out. And exactly the same thing is going to happen with trig as well. Just change x to cosine. And now it's a trig conjugate. All right, so generally I told you to start with the side that looks more complicated. Which side looks more complicated here? I'd say it's really the same level of complexity on each side. I don't think one side clearly looks simpler than the other. So in that case, you could start with either side. So we got to pick if we want to change the left into the right or the other way around. How do we want to do it? We're going to take the left and change it into the what's on the right. Okay? So when we're done, this is what we want to get. Could I change things to sines and cosines here? Already is. Could I find a common denominator? Why not? Why can't you find a common denominator?
I mean, you just have to make it into two different fractions.
You know, it has a common denominator. You have something in the top and you have something in the bottom. You just have one fraction. You don't have it split into two. So it's one fraction. Unless you have multiple fractions, you don't have multiple denominators. So the only thing I can try is the conjugate. So what would be the conjugate here? Would I be working with the top or the bottom?
Bottom.
Yeah, the bottom. Its conjugate's got to have at least two terms. All right? And what would be the conjugate of what's in the bottom? Yeah, 1 plus sine. So we're going to multiply this out. But I'm only going to multiply it out in the bottom. So you might think, well, didn't we have one in the top where we distributed? Kind of like we used the distributive property before, and we did. But if you distribute cosine, it's actually going to make the problem harder. You can, it's just, you're going to distribute it, and then we're going to undo that in the next step. And the only reason I know that is just from practicing. So sometimes kind of the example I give is it's kind of like playing chess when you do these, if you've ever played that. You kind of have to think a couple steps ahead. So the move you're doing now is to set you up for something you're going to do in a couple steps, which is a hard thing to do without practice. So just leave the top, and you'll see why in a second. And now the bottom, we'll do it out, because they're conjugates. Anytime you have conjugates, always multiply them out. So we got 1 times 1, which is 1. And then we've got 1 times sine, 1 times negative sine. What happens there? That cancels. What's a negative times a positive? Negative. Sine times sine. Sine squared. Now, that isn't exactly something we had, but if you look at this, does anybody see what identity that 1 minus sine squared is similar to? The first, which one?
The sine squared times plus cosine.
Yeah. If you just take and subtract sine squared and subtract sine squared, on the left you would have cosine squared, and on the right you have exactly what we have in our problem, 1 minus sine squared. So what is 1 minus sine squared equal to? 1 minus sine squared is cosine squared. Okay. So I'm just going to cross this out and replace it with a cosine squared. Now, does anybody see what I can do here? And this is why I said don't distribute it. Right, we have a 1 cosine in the top, we have 1 cosine in the bottom. Well, we have 2. But we can cancel 1 from the top, and we can cancel 1 from the bottom. So what am I left with in the top? 1 plus sine. And what's in the bottom? Just cosine. And if you go back up and look, 1 plus sine over cosine, that's exactly what we were supposed to get. So that kind of problem doesn't really simplify much, but you already knew that before you started it. This is what you started with, this is what you finished with. We knew not much was going to simplify, it was just going to kind of flip over and this changed to a minus to a plus. Okay, so that's a common kind of problem. Again, I wouldn't argue that we really simplified anything, but we did verify something. Any questions on that? This is pretty much exactly the same kind of thing. Any questions on how you would do this one? It's almost the exact same problem. It flips and something changes from a minus to a plus. The only thing I notice here is I have a cosecant and a minus 1. So when I multiply by the conjugate, I'm not going to be using, where is it? Probably not going to be using this first identity. Probably going to be using this one. Because I have a 1 and a cosecant. So when you FOIL it, you're going to end up with a cosecant squared. Okay, so it's going to be this one somehow. Okay. Any questions on how you do that one? All right. All right, let's, it's not that many. Let's try this one. All right, so let's see. Any suggestions on what I could try here? How about what side do we want to start with? The left? I would probably start with the right. To me, that looks a little more complicated than the left, just because you have some stuff in the top and the bottom to simplify. And this is a problem that there's a very easy way to do it. And then there's a way that takes a much longer time. And I don't remember which one was which. So, I'll blame you guys. How do you want to start this problem? Any suggestions on what we do first? Okay, we know that way will always work. I just don't remember if it's the fastest way in this problem, but it will work. So what is tangent? So we got sine over cosine. What's cotangent? Cosine over sine. And actually, right the way I said it, cosine over sine. All right, and then the bottom is the same thing, with just a plus sign. So it's sine over cosine plus cosine over sine. Okay, this might have been a problem where I could have tried the conjugate. I could have tried multiplying top and bottom by like tangent minus cotangent. And I think that probably would have worked out nicer, but let's try this and see what happens. What's the common denominator in both the top and the bottom? Sine times cosine. Yep, so it's going to be a sine cosine in the top and in the bottom. What is that denominator missing to make it the common denominator? Sine. So I'm going to multiply top and bottom by sine. What is that denominator missing? Cosine. So we're going to multiply top and bottom by cosine. All right, and now the bottom is the same thing, yeah. Sine squared plus cosine squared. All right, at least in the bottom, I see something I can simplify. What can I simplify in the bottom? Bottom fraction. Amanda?
Sine squared plus cosine squared equals 1.
Yeah, you can simplify all that into a 1. So I've got sine squared minus cosine squared. I don't like sine squared minus cosine squared because there's not a lot you can do with that. Plus is good, minus not as good. Over sine cosine. And instead of dividing by a fraction, I can just multiply by the reciprocal. So I've got sine cosine over 1. Okay. And just get rid of this. Anything there that I can cancel out?
Denominator on the left side and the right side.
Yeah, we can cancel out, so what we're left with is this at this point. Now, we're supposed to end up with tangent and secant. So I don't think we've made any mistake yet. I'm just not sure we've quite figured it out. What is sine squared the same as? Anybody think of how I could rewrite that? I'll give you a hint. I'm trying to get tangent involved, okay? Because the final answer has tangent. So tangent is sine over cosine. So does anyone see how you could? Yeah, we'll finish that one later. Yeah. On that last problem, we did not pick the right way to do it. It's not that the way we picked won't work. It will, but it was not the best way to do it. Okay, so that's the homework on 407. I'll take a look at that next time we have class, which will be in a couple weeks.